Welcome to Share the Knowledge.
Good morning to everyone. In today's video, we will see the analysis of impulse generator. Okay, one circuit of our impulse generator. So already in previous classes, we see the simple analysis for our RLC circuits. Okay, here in today's video, the circuit will be similar fashion, but we modify only the load side circuit. Okay, this is your spark gap and this is your combination of resistor and capacitor. This is your C1 and this is your R1 and C2 and R2 and C2. So initially this capacitor will be charged for the voltage of V, for the DC voltage D. Okay, the same circuit will be represented like this also. There is no variation. Both are same. Okay, the first circuit will be represented in CL Wadhwa and the second circuit is represented in MS Naidu. Both representations are correct. Okay, the only variation, they just rearrange the elements. They rearrange the elements without modifying the impedance of the circuits. Okay, this is your spark gap. So whatever your capacitor is initially charged to your voltage V. Okay, DC voltage V. Once the capacitor starts discharges, when this spark gap discharges, okay, conduction path will be formed and the circuit becomes closed circuit. Okay, so here the capacitor will act as source here. So please note those notations. Your capacitor C1 is charged. Capacitor is C1 only charged. So up to the magnitude of your capital V, and whereas coming to your C2, it is uncharged circuit. It is an uncharged circuit. Okay, so please note of these 2 points. Once the closed path is formed, we are going to analyze. So we are considering the total impedances. So the total impedances I am considering in the S domain. This is C1 of S, C2 of S, where the resistors will be common. So these two are in series. So 1 divided by C1 of S plus R1, and this will be your parallel combination. So parallel combination will be R2 into 1 divided by C2 of S divided by C2 of S. So R2 equals to 1 divided by R2 C2 S. So this entire parallel combination will be given as R2 divided by 1 plus R2 C2 S. Okay, take the denominator term 1 plus R2 C2 S C1 of S. So do this simple mathematics, rearrange the terms. Okay, so your S coefficients as a square coefficient R1, R2, C1, C2 plus your S coefficient R1, C1, R1, C1, R2, C2 plus R2, C1 plus 1. Okay, so this is your Z of S. Okay, Once the closed circuit is formed and current flowing through a circuit, I am interested to find out what will be the current in circuit. So I of s. So I am considering V naught. Okay, V naught will be the voltage. So V naught. So it is in constant AC. It will be 1 divided by S. So ZS. Okay, so try to arrange this terms. So enter your denominator. So I'm not rewriting this. So enter this denominator. Try to replace here. So once I got, I'm interested to find out what is the voltage drop across your capacitors. What will be the voltage drop across your capacitors? So V of S equals to I of S into. So since it is in a parallel combination, you consider. Okay. So try to replace this IS value here. So cancel over this and your S term will be cancelled over. So V naught R2C1 multiplied by your entire quadratic equation. So taken this term also, the magnitude C1 C2. So it will be S into R1 C1 plus R2 C2 plus R2 C1 divided by R1 R2 C1 C2, and this will be your R1 R2 C1 C2. Okay, so try to find out this quadratic equation, roots for this quadratic equation. So already we know that minus b plus or minus root over b square minus 4ac divided by 2a. We know that a is your s square coefficient, b is your s coefficient, and c is your constant coefficients. So try to replace those things and find out what will be the thing. So once I place this, it will be your R1 C1 plus R2 C2 plus R2 C1 divided by R1 R2 C1 C2 plus or minus root over. So here 1 by 2, because s square is 1 now, so 1 by 2 I just simply take it. So entire this b square R2 C2 plus R2 C1 divided by R1 R2 C1 C2. I'm not solving entire thing, so minus 4 divided by R1 R2 C1 C2. Instead of going for this calculation, so I'm just taking this. Simply assume this term. Simply assume this term as your alpha and this term is your beta. Okay, this term as beta. Okay, so your roots will be, okay, your roots will be minus alpha plus or minus beta. Okay, so minus alpha plus beta and minus alpha minus beta will be your roots. R1 and C2. So your roots will be s minus alpha plus beta minus beta. So these will be your roots. So already we know that we can do the partial fractions for it. So don't modify any changes here. A simple sign change also will leads to the what we call okay. So the expression will be s minus alpha, sorry, s plus alpha plus beta plus b into s plus alpha minus beta. So compare your s terms, a plus b equals to 0, so b equals to minus a. Similarly compare your, sorry, this is your s terms, and you compare your constant terms. So a alpha plus a beta plus b alpha plus b beta equals to 1. So either you may change entire term or any one also it will be acceptable. So a alpha minus b beta, okay, minus a alpha plus minus b. So this will be your minus b, so this will be your minus b. So minus b beta equals to 1, so it will be cancelled over here. So minus 2b beta equals to 1, that means from beta equals to minus 1 by 2. So b equals to minus 1 by 2 beta. So when b equals to minus 1 by 2 beta, then a will be your 1 by 2 beta. So try to substitute in your equation. So v of s equals to v naught divided by r1 c2 1 by 2 beta 1 divided by s plus alpha minus beta minus 1 divided by s plus alpha plus beta. So already we know our inverse Laplace transformation. So try to apply this inverse Laplace transformation. This entire thing will be your magnitude. So r1 c2 2 beta, take the inverse Laplace of here. So e power minus alpha minus beta t minus e power minus alpha plus beta into t. Okay, so whatever this entire thing, we can give it a magnitude. Okay, magnitude, not the peak value, it is just a magnitude. Okay, minus e power. So this is your impulse equation what we discussed previously. what we discussed previously. So this is your term. Again we have to analyze further wavefront and tail. Okay, wavefront and tail. So keep it this equation. Okay, keep this equation. V of t equals to Vn of e power minus alpha minus beta t minus e power alpha plus beta into t. Okay, so up to here if you're clear, it is very easy for the rest of the discussions. Take the differentiation of this equation. So dvt by dt equals to your magnitude Vn. So there is no and take this is the t element. So it will be minus alpha minus beta e power minus alpha minus beta into t minus, so minus of minus plus alpha plus beta e power minus alpha plus beta into t. Okay, so when you equate this one for 0, for maximum value, if we equate for this 0. So when we equate this 0, this term, okay, this term may be 0 because your magnitude won't be 0. So this will be the 0. So I'm just equating this one for the 0 of t. So when I taken from RHS side, okay, just okay. So I am assuming here. Okay, T1 is the time. To reach your maximum value. T1 is the time here. So alpha minus beta e power minus T1 equals to alpha plus beta e power. So rearrange the elements. Alpha minus beta divided by alpha plus beta e power minus alpha plus beta t1 divided by e power minus alpha minus beta t1. Okay, so rearrange this alpha. So all the terms having the t1, so I'm just beta. So when taking this one as numerator, it will be your plus alpha and minus beta of t1. So it will be cancel over. So it will be your e power minus 2 beta t1. Okay, so negative term, either way we can do. So take the logarithmic on both sides. 2 beta t1 equals to ln of alpha minus beta divided by alpha plus beta. So from this the t1 value, t1 equals to 1 by 2 beta. So I'm negative term and just inverse the logarithmic alpha plus beta divided by alpha minus beta. So this is the expression for your time to reach your maximum value. This is t1. When we go for your wave time, tail time, please note tail time t2, where the magnitude will be your half of the value. Okay, magnitude will be your half of the value. So try to replace your expression. Already we know for your wave our voltage expression. We know our voltage expression. Here we are replacing. So this is your Vn and e power minus alpha. This is your T2. Okay, T2. Okay, so here compared to your V1 expression, the magnitude will be reduces by 2. Okay, your magnitude will be reduces by 2. So I am replacing this T1 e power minus alpha plus beta T2. Okay, so your expression. So whatever this term, okay, whatever this term will be very negligible. It will be very negligible. So I'm just simply neglect this. Okay, exponential of negative logarithmic value, it will be very small. So I'm just neglecting this one. So if you rearrange the term beta T1, so whatever this T1 is there, we can written in terms of some magnitude, multiply of your time constant T1. Okay, so I'm replacing this for solving, because here we are having two unknowns, one expression, so it is difficult to calculate. So I'm considering that assumption minus alpha plus beta T1. So whatever these expressions are T1 here. Okay, so try to rearrange this terms or multiply with e power, multiply with e power alpha minus beta T1. Okay, so multiply this expression on both sides with T1 multiplied by e power alpha minus beta into T1 on both sides. If I multiply here, it will be cancel over and reaches to 1. Alpha plus beta T1 e power alpha minus beta T1 2 into. So if I consider any case, so it will be e power minus alpha minus beta. If I take it as common, minus 1 will be there. So if I consider minus and minus, it will be k minus 1 T1. If anybody doesn't understand this expression, you just simply take the minus 1 factor. So 1 minus will be there for your minus alpha minus beta, and another minus will be for your T1. So you can get this. So 1 minus e power so minus plus, it will be cancel over, so it will be minus 2 beta T1. Okay, so your expression for minus alpha minus beta k minus 1 T1 power e power na, so it will be 1 minus e power minus 2 beta T1 divided by 2. So take the logarithmic and inverse of it. So alpha minus beta k minus 1 T1 equals to log of 2 divided by 1 minus e power minus 2 beta T1. So from this we can get an expression for your T1. So alpha minus beta, here itself I am mentioning, I am just considering. So 1 divided by k minus 1 t1 log of this expression, complete expression here. If you observe this denominator term, it is also very neglectable, so it will be almost equated to 1, almost equated to 1 from this. So the expression is given as 0.7 divided by k minus 1 into t1, alpha minus beta as 0.7 divided by k minus 1 into t1. So this is the analysis of your circuit 1. This is the analysis of your circuit 1. So this expression, whatever this expression is there, it will be verified for the different impulse circuits. There we can retrieve some key points. So whatever this C1 is there, it will be a fixed quantity. The C2 can be varied. Whenever the C2 quantity is varying, automatically the shape of your impulse, because your impulse, your impulse expression is depending upon your R1 and C2 values. So there will be an effect of your values. There will be effect of your values of your C1, C2, R1 and R2. So mostly whatever this R1 and R2 are limited, and the ratio of your capacitors C1 and C2 are also limited. Okay, so this is the analysis of your circuit 1, first model. Okay, this is the analysis of your model 1. Okay, in another video we will see what will be the impact, what will be the effect of your inductors, capacitors in your impulse waveform as separate. This is only the analysis part, how we are retrieving the magnitude expression, of your impulse waveform. This is for circuit A. This is for your circuit. This is your circuit. Please remember, this will be your RC circuit. This is for RC circuit.